Time for us to get started. So, I want to do just a little bit of brief review just because I want you to see the big picture and not just get lost in the little details. In other words, I want you to see the forest instead of just the trees. Okay? That's what I'm saying. All right, so the last time we met, we were talking about regulation of GFR, which stands for glomerular filtration rate. That's how fast the kidneys are filtering the blood. Okay? It's important that GFR is high enough to filter the blood and remove the waste, so waste don't build up, but you don't want it too fast, because if you filter the blood too quickly, then you lose valuable water and electrolytes. Okay? So there's three different kinds of mechanisms, or three categories of mechanisms, I suppose you could say. There's four different mechanisms. The first is renal autoregulation. Renal autoregulation regulates GFR in the short term. And it's actually a way that the afferent arteriole controls its own diameter. And by controlling its own diameter, that regulates GFR, because if the afferent arteriole dilates and expands its diameter, that allows more blood to flow into the glomerulus, that increases glomerular filtration rate. If it becomes constricted, that narrows its diameter and increases resistance, that decreases blood flow into the glomerulus, which decreases GFR. Okay? So there's two mechanisms we went over of renal autoregulation. The first, very simple, it's called the myogenic mechanism. That's where if blood pressure increases, it causes the afferent arteriole to stretch. In response to stretch, it causes it to constrict, and that decreases GFR. Okay. The other one's called tubulo-glomerular feedback. That's a lot more complicated mechanism. That involves a monitoring of the filtrate in the distal convoluted tubule by cells in the distal convoluted tubule called the macula densa. If it detects an increase in sodium in the distal convoluted tubule, that's a signal that GFR is too high. If GFR is too high, then the filtrate's going to move through the tubules more quickly. It's not going to give enough time for the sodium to be reabsorbed, so sodium levels become higher. So if that happens, then the macula densa sends a signal that again causes the afferent arteriole to constrict, and that decreases GFR. Okay, so both of those can regulate GFR very quickly in the short term. Okay. A second mechanism is sympathetic control. One situation where that occurs is during exercise, because during exercise, or even the anticipation of exercise, that causes an increase in sympathetic activity, activity of the sympathetic nervous system. There's sympathetic fibers that supply the kidney, and that causes vasoconstriction of the afferent arteriole, which reduces GFR. So the purpose of that is to divert blood away from the kidneys and to your skeletal muscles and your brain, and because those are the parts of your body that are needed during strenuous exercise. And finally, today what we're going to go over is hormonal control. Hormonal control does a couple of things. One of them is that it can regulate blood pressure over the longer term. Okay, it's a hormonal mechanism, so it's a little bit slower, but it can regulate blood pressure over the long term. And in doing so, that also affects GFR, okay? If you lower blood pressure, that's going to lower GFR. If blood pressure increases, that's going to increase GFR. Okay. So hormonal control involves a fairly complex mechanism, but it's a very important one, and it's a good one to know because there's a lot of drugs that affect blood pressure that affect some of the components of this system. It's called the renin-angiotensin-aldosterone mechanism, or the RAS mechanism for short. Okay. Now, it's important that you properly pronounce the word renin. It's pronounced renin with a long E, not renin. Okay. Let me show you the difference in the two words. Okay. Renin, which is part of this system, is spelled R-E-N-I-N. Okay. There's another similar word that sometimes students get it confused with called renin. Renin is an enzyme that is found in young mammals that causes milk to solidify or curdle. And that slows down digestion of milk, which allows young animals to absorb nutrients better. Okay. Renin is also used, it's an enzyme that's also used in the production of cheese. They mix it with milk and it curdles the milk and it turns it into solids that are converted into cheese. Renin is an enzyme that's produced by the juxtaglomerular cells in the kidney that regulates blood pressure. It also can regulate sodium. Okay? So let's look at a diagram of this renin-angiotensin-aldosterone system. Okay, so there are really several organs involved in this system, the main one being the kidney. And the kidney is what releases renin in response to either low blood pressure or high sodium levels. So it regulates both water as well as sodium. The reason it regulates both of those is because water reabsorption, sodium reabsorption are actually very closely tied together. Because the way water is reabsorbed by the kidneys is by reabsorbing sodium. You reabsorb sodium out of the filtrate and in the interstitial fluid. That increases the osmolarity of the interstitial fluid. That draws water out of the tubules. And so both sodium, whenever sodium is reabsorbed, water is also reabsorbed. So just remember the phrase, water always follows sodium. Wherever sodium is transported, water is also transported in the same direction. Okay? So in response to either a drop in blood pressure or a drop in sodium, increase in sodium, and the one situation where you get an increase in sodium levels of the blood is if you get dehydrated. If you get dehydrated, that one way to get dehydrated is you lose too much water. Like you lose water in the form of sweat. If you lose water but not sodium, then the sodium levels of your blood are going to go up. And so that's a sign of low blood volume. Low blood volume causes low blood pressure. Okay? So either a drop in blood pressure or an increase in sodium causes the kidneys to release the enzyme renin. Okay? Now, there's also a protein that's produced by the liver that's called angiotensinogen. The liver produces a lot of proteins. If you remember, the liver also produces a lot of pro-clotting factors, like, let's see, let me shift gears here, go back to earlier in the semester. Fibrinogen, for example. Fibrinogen is a protein that's secreted by the liver, and it's converted to fibrin by the enzyme thrombin. Prothrombin is another enzyme that's produced by the liver. So liver also produces angiotensinogen, which is a protein that's 453 amino acids long. Okay, so the liver always secretes angiotensinogen in the blood. So angiotensinogen is always circulating in the blood, just like fibrinogen and a lot of those other clotting factors that are produced by the liver. Okay, so what renin does, renin breaks off a part of angiotensinogen. It cleaves angiotensinogen. To cleave is to cut, okay? So it cuts off a part of that, and it cuts off a 10 amino acid sequence of angiotensinogen. That 10 amino acids that gets cut off is called angiotensin 1. Okay? So angiotensin 1 is now in the blood because this renin, which was released in the bloodstream by the kidneys, that cuts off a part of angiotensinogen, that forms angiotensin 1. Okay. Now, there's another enzyme that's found in high concentration in the lungs. It's found mostly in the pulmonary capillaries of the lungs, the blood vessels of the lungs. But it's also found in other blood vessels in other parts of the body. And so actually it should say all blood vessels. They used to think this enzyme was only found in the lungs, but they realized quite a while ago it's actually found in the lining of almost all blood vessels. But it is in higher concentration of lungs. This enzyme is called angiotensin converting enzyme, or ACE for short. Okay. So angiotensin converting enzyme breaks off a part of angiotensin 1 to form angiotensin 2. Angiotensin 2 is a very potent vasoconstrictor. So it causes vasoconstriction in blood vessels throughout the body. And that increases peripheral resistance, which increases blood pressure. That brings blood pressure back up if your blood pressure is too low. Okay. It doesn't happen real fast, though, because this mechanism does take time to occur. Okay, so this is a slower mechanism. In addition, angiotensin 2 stimulates the release of antidiuretic hormone, or ADH, from the posterior pituitary. And ADH increases water reabsorption by the distal tubules of the nephron, mostly by the collecting ducts of the nephron. So that increases water reabsorption, which again brings blood volume back up, and that increases blood pressure. In addition, ADH also increases thirst. It stimulates thirst, so you have an urge to drink more water. That also is going to bring your blood volume back up again. It's going to bring up blood pressure. Okay. And then thirdly, angiotensin 2 also stimulates the release of another hormone from the adrenal cortex. Now remember, the adrenal glands sit right on top of the kidneys. There's two parts to the adrenal glands. There's the adrenal cortex, which secretes over a dozen different hormones. And then there's the adrenal medulla. The adrenal medulla is actually part of our sympathetic division of our autonomic nervous system. So the adrenal medulla secretes epinephrine, or adrenaline is another name for it, which produces a mass activation of our sympathetic nervous system. Okay, so this angiotensin 2 stimulates the release of a hormone from the adrenal cortex called aldosterone. Aldosterone increases the reabsorption of both sodium and water, mainly in the distal convoluted tubule. Okay, so that causes an increase of sodium, which causes an increase in reabsorption of water. That also brings blood volume back up and increases blood pressure. So these are all effects that are in response to either a drop in blood pressure or an increase in sodium concentration of the blood. Like I said, that increase in sodium concentration is sort of a sign that you're dehydrated, you lost more water than sodium, and that's going to decrease your blood volume. And if your blood volume decreases, that's going to decrease blood pressure. Okay. So, just briefly, the way this works is that in response to a drop in blood pressure, kidneys secrete renin. Renin converts angiotensinogen to angiotensin-1. Angiotensin-1 is converted to angiotensin-2 by angiotensin-converting enzyme. Angiotensin-2 is a potent vasoconstrictor, so it increases blood pressure, which increases GFR. It also stimulates the release of antidiuretic hormone, which causes more reabsorption of water by the kidneys. And angiotensin-2 stimulates aldosterone, which increases both sodium and water reabsorption in the distal convoluted tubules. Okay, so all those things help to bring blood pressure back up, which increases GFR. All right. Now, one other reason for knowing this system is there are some drugs that are used to lower blood pressure that affect a part of the system. Okay? One of them is there's a class of drugs called ACE inhibitors. ACE inhibitors, that stands for angiotensin converting enzyme inhibitors. That inhibits the activity of this angiotensin converting enzyme. It blocks it from converting angiotensin-1 to angiotensin-2. If you inhibit that enzyme, that's going to lower the concentration of angiotensin-2. Since angiotensin-2 is a vasoconstrictor, that's going to cause less vasoconstriction, and so that's going to lower blood pressure, because vasoconstriction increases peripheral resistance, that increases blood pressure. So that's just one of several different types of blood pressure medications that they can use. Sometimes doctors will have to prescribe one over another because sometimes blood pressure medications have side effects, undesirable side effects. Okay? So if a person has a side effects to one, they can switch that person to another. Another one is calcium blockers, because calcium blockers can decrease the contractility of the heart. It decreases cardiac output, which decreases blood pressure. That's another one, though. All right, any questions? Okay, so I would recommend just practicing writing this out. I'm not going to have you do this here in class, but practice writing it out. I don't know if any of you have gone through this in other classes, but sometimes I have nursing students who say, "Oh yeah, we just went over that in nursing," and so they've heard it more than once. I don't know if that's the case this year. I see somebody nodding. Are you nodding into that or something else? Okay, never mind. Okay. All right. So just to recapitulate or review, angiotensin-2, once it's produced by the system in response to a drop in blood pressure, it's a potent vasoconstrictor which raises blood pressure throughout the body. It constricts the efferent arteriole, which raises the GFR despite low blood pressure. And it lowers the blood pressure in peritubular capillaries, enhancing reabsorption of sodium and water. These are sort of secondary effects. Angiotensin-2, actually one of its main effects is that it stimulates the release of aldosterone by the adrenal cortex, and that increases active reabsorption of sodium and water in the distal convoluted tubule and also in the collecting ducts. Angiotensin II also stimulates the posterior pituitary to secrete ADH, which promotes water reabsorption by the collecting ducts, and it also stimulates thirst, which increases your total body water when you drink, and that also increases blood pressure. Okay? All right, that's the end of this section of chapter 23. So let's move on to the next one. By the way, I originally had the PowerPoint slides for this chapter broken up according to the different sections in the chapter, and so I put those on Canvas. I also combined them all into one file that says this is the entire chapter 23. So there's really two different versions of this. There's one of them with this all put together. There's also separate pieces that are broken up. So there may be a little bit of redundancy on it. So now that we've seen how filtration is regulated, in this next section we're going to look to see how the majority of useful substances are reabsorbed in the nephron. Okay? Before we do that though, let's do a review question. Now that we've gone over that RAS system, okay, so in response to elevated levels of angiotensin II, aldosterone levels do what? Do they decrease or do they increase?
So Woolclap's not actually working.
It's not working? No.
Oh, yeah. No.
Are you putting in the new code? Message. Oh, huh. Okay.
It wants us to log into
Let me
game
see if I
University.
can fix that. Give me a second here.
Yeah, you have to be under Ghent University. Whatever that one is.
It might be a problem from my end here.
I think it is, because that looks different than what it is. But, I have no clue, because this one we haven't talked about either. This chapter 23 one. Yeah, I don't know.
What do you mean?
Maybe the problem is I'm not logged in. Be logged in.
Haven't I do
Collapse.
this?
Well, that's all I've read. Better than me. Yeah, you've done better than both of us.
Check your grade again. I have a 91.
I only have the same score.
Okay, looks like there's a glitch in the system. It may be that just
I was 90.
part of the WooClap system is down, because I'm getting an error too. It said failed to fetch the event. So I'm not sure. So we'll have to skip that. So we'll just go over these questions then. So this first one, this is not the first one, let's see. Okay, so angiotensin II stimulates the release of aldosterone from the adrenal cortex, so that would increase the concentration of aldosterone. Aldosterone then stimulates so that's the next question here is what does aldosterone do? And again, it may not be working. So increased aldosterone levels cause an increase in sodium reabsorption and also water reabsorption. So number one would be the correct answer for that. Okay, so what we're going to do next, this next part of chapter 23, we're going to look at the reabsorption of water and sodium and nutrients like glucose and amino acids in the tubules of the nephron. Okay, so the part of the nephron where most of the useful substances are reabsorbed is in the proximal convoluted tubule. That's the first part of the nephron after the renal corpuscle. Okay, so right after the blood's been filtered, that filtrate goes first in the proximal convoluted tubule. About 65 to 70% of that filtrate is reabsorbed in that first part, that first tubular part of the nephron. And it also secretes substances from the blood into the tubule. Okay, so there's two ways substances can get into the filtrate. It can get it from filtration, but there's also a process called secretion where substances that didn't get filtered, that remained in the paratubular capillaries, can be actively transported from the paratubular capillaries into the proximal convoluted tubule. So that process is called secretion. Secretion is the opposite of reabsorption. Reabsorption is movement of useful substances out of the tubules and back into the blood, and it goes into the paratubular capillaries. So proximal convoluted tubule has a very large absorptive surface area because on the luminal surface of the cells that form the walls of the proximal convoluted tubule, there are numerous microvilli which provide for a very large surface area. And you need a large surface area for transport. Transport mechanisms in the proximal convoluted tubule, we'll see some of these in action here just a little bit. It includes active transport, co-transport, both symport and antiport, as well as diffusion. The cells of the proximal convoluted tubule contain abundant mitochondria to supply ATP for active transport, because you get lots of active transport of sodium in the proximal convoluted tubule. Sodium is reabsorbed back into the blood. So the proximal convoluted tubule, even though it's a very small part of the nephron, there are a lot of them, there are millions of those nephrons in the kidneys. That accounts for a very large proportion of your body's ATP usage. It accounts for 6% of one's resting ATP usage. So it's a very metabolically active part of your kidneys. So sodium reabsorption is the key to reabsorption of almost everything else by the proximal convoluted tubule. Reabsorption of sodium creates an osmotic gradient that drives reabsorption of water. And we'll see a diagram so you can sort of see a graphical depiction of this, how it works. And then other substances are reabsorbed or secreted by either symport or antiport mechanisms that rely on that sodium gradient. So they're co-transport processes that use that sodium gradient to reabsorb things like glucose and amino acids, or secretion of hydrogen ions. So this is a diagram. I took this from a different source just because I liked it better than the one that's in your textbook. One in your textbook I think is a lot, they try to cram too much in one diagram. So I picked one that was just focused mainly on sodium reabsorption. So let me just get you oriented to this, because you have to understand what's what on this diagram to understand what's going on. So over here, this is the lumen of the proximal convoluted tubule. That's the hollow portion of the tubule where the filtrate is located. That filtrate, remember, was produced by filtration between the glomerulus and the glomerular capsule in the renal corpuscle. So this is filtrate. Has about the same composition of the plasma, except it's missing larger proteins and large molecules. Okay, so these are the cells that make up one side of the walls of the proximal convoluted tubule. And then this is the interstitial fluid out here, outside of the proximal convoluted tubule. And this is one of the paratubular capillaries. Paratubular capillaries receive blood from the efferent arteriole. So after the blood's been filtered, it goes out of the renal corpuscle through the efferent arteriole. That efferent arteriole, though, then branches out and it forms the paratubular capillaries that surround the tubules of the nephron. Okay? So the whole key to this process is a form of primary active transport that's found in what's called the basolateral membrane. This membrane right along here, along the outside of the tubule and also on the sides of these cells, this is called the basolateral membrane. This membrane over here next to the filtrate, that's the luminal membrane. Okay. So in this basolateral membrane, there are sodium-potassium ATPase pumps, which is a form of primary active transport. It simultaneously transports 3 sodium out of the cells that make up the walls of the proximal convoluted tubule. At the same time, or about the same time, it transports 2 potassium into those cells that form the walls of the proximal convoluted tubule. Okay. So what this does is it increases the osmolarity of this interstitial fluid. Okay? And that's important. It also decreases the concentration of sodium inside the cells that make up the walls of the proximal convoluted tubule. So you have a very low concentration of sodium in here, okay, because sodium is constantly being pumped out into the interstitial fluid. So you have a sodium gradient between the intracellular fluid and the extracellular fluid out here. All right. So since the concentration of sodium is very low inside those cells that make up the walls of the proximal convoluted tubule, sodium can diffuse via facilitated diffusion from the filtrate into the cell, because the concentration of sodium is always lower inside the cell than it is in the filtrate, because sodium is constantly being pumped out. So you have a very low concentration here. So you have what's called a standing gradient of sodium. The concentration of sodium is always lower inside these cells than it is in the filtrate. So sodium can move then by facilitated diffusion from the filtrate into the cell. Once that sodium gets in the cell, it's then pumped out by the sodium-potassium pumps that's in the outside of those cells. Okay? And so what that does, it ends up transporting the sodium from the filtrate out into the interstitial fluid. Okay? Then that sodium can be picked up by these paratubular capillaries. All right? Now, as a consequence of that sodium gradient, which is higher now in the interstitial fluid than it is in the filtrate, that draws water out of the filtrate, and water can actually go in between these cells just by osmosis, and that drives reabsorption of water. And there are other substances like glucose and amino acids that can be reabsorbed by symport proteins that are in the luminal membrane. Like this X right here, that might be glucose. So glucose rides on this sodium reabsorption. It kind of gets carried along with the sodium when it's reabsorbed, or amino acids, or anything else that might be useful. Okay, so that accounts for about 65 to 70% of all the sodium, water, glucose, amino acids that's reabsorbed by the kidneys. It all occurs right in that first part. Okay. So, just to put this into words instead of looking at a diagram, active transport of sodium into the interstitial fluid increases the osmolarity of that interstitial fluid. That creates an osmotic gradient that draws water out of the tubules and into the interstitial space. Water also can go in between the cells. That's called the transcellular, or water through the transcellular route is the right route that goes through the cells that make up the walls of the tubule. So that could happen because there are water channels in the membrane of those cells that are called aquaporins. And that allows water to diffuse by osmosis from the filtrate into the interstitial fluid. So the net effect of this reabsorption of the proximal convoluted tubule, because equal amounts of solute and water are reabsorbed, the osmolarity of the filtrate remains unchanged. It stays about 300 milliosmoles, which is about the osmolarity of the plasma in the blood, but the volume is reduced by about 2/3. So you have a lot less volume of filtrate, but the osmolarity stays the same. The composition does change though, because you're reabsorbing useful substances, but not the waste products. So you end up with a higher concentration of waste in the filtrate, but a lower concentration of water and, well, not a lower concentration of water, but you have fewer water molecules, fewer sodium molecules. So this reabsorption of water in the proximal convoluted tubule is occurring all the time. It's not regulated. The only thing that regulates it is the activity of those sodium-potassium pumps, and those sodium-potassium ATPase pumps are working all the time. They don't stop. And so this reabsorption of water and sodium occurs in the proximal convoluted tubule continuously. So it's called obligatory water reabsorption. It's water reabsorption that can't be regulated. But we almost always need water because we live on dry land, and the air is drier than our body, so we're constantly losing water. And so water is a useful and needed substance. And so proximal convoluted tubule reabsorbs approximately 2/3 of all the water that gets filtered by our kidneys. So after leaving the tubular epithelium and entering the interstitial space, water and solutes are taken up by the peritubular capillaries. And the uptake of water is by osmosis. And electrolytes like sodium and a few others, sodium and chloride, some potassium, it kind of just gets dragged along by the osmosis of water. And that process it's not understood very well, but they have a name for it, it's called solvent drag. Some of the sodium and chloride and potassium dissolves in the water, and when water gets reabsorbed by osmosis, those electrolytes just get carried with it. Okay, so they're just, it's called solvent drag. Okay. Now, the reason water can be reabsorbed in the peritubular capillaries by osmosis is because the blood that flows into the peritubular capillaries has just come out of the efferent arteriole, and it's just coming out of the glomerulus where filtration has occurred. And so water and small molecules, so a lot of water gets filtered in the renal corpuscle, because a lot of the water gets filtered and goes into the tubules, but the blood cells and large proteins don't get filtered. They stay in the blood. Then that blood that's lost a lot of its water is going into those peritubular capillaries. It has a higher osmolarity because it's lost most of its water through filtration. Because of that higher osmolarity of the blood in the peritubular capillaries, that allows the water to be reabsorbed into the peritubular capillaries by osmosis. Okay, so it's kind of a neat system. So the net result then is much of the water leaving the glomerulus. Well, the reason that the blood in the peritubular capillaries has a higher osmolarity is because it's lost most of its water in the that's gone through the glomerulus, while most of the protein in the blood remains in there prior to flowing into the peritubular capillaries. So it has a higher osmolarity because it's lost water through filtration. All right. Now, some substances like glucose are reabsorbed by symport proteins that are in a limited number. There's a finite number of glucose transporters that use the sodium gradient to reabsorb glucose and things like amino acids. Because there's a limited number of these symport proteins, there's a maximum rate at which nutrients like glucose can be reabsorbed. Because once all of those symport proteins are being used to reabsorb glucose, then you can't reabsorb any more at a faster rate. And so for reabsorption of nutrients like glucose and amino acids, there's a maximum rate of transport that occurs, which is called the transport maximum for that particular molecule. And so the fact that there's a transport maximum for glucose explains why people that have diabetes mellitus, where they have really high blood levels of glucose, that's why they end up with higher levels of glucose in their urine. Because there's a transport maximum for glucose, there's a finite number of glucose transporters. The kidneys can't reabsorb all the glucose that's been filtered. And since it can't reabsorb all the glucose that gets filtered, some of the glucose stays in the filtrate and it gets excreted with urine. That's why if you test someone's urine that has diabetes mellitus, it's going to test positive for glucose. Whereas someone who's not diabetic, there's going to be little to no glucose in the urine. Normally, it would be no detectable glucose to just a trace glucose. But if there's high levels, that's a sign of diabetes mellitus. Because it's just because blood levels are so high that not all of the glucose can be reabsorbed. All right. Now, in addition, secretion can also occur in the proximal convoluted tubule and also in the distal convoluted tubule. So, secretion is the opposite of reabsorption. And the secretion of other substances like hydrogen ions, which are basically waste that our body needs to get rid of if we have too many hydrogen ions, or also secretion of waste that didn't get filtered, like urea and uric acid and creatinine, that can occur via secretion. Toxins, toxic substances. Those could be transported into the filtrate using antiport proteins. That the antiproteins are still using the sodium gradient, which is driven by that standing gradient, but the transport is in the opposite direction. So tubular secretion is the transport of waste and hydrogen ions into the tubules of the nephron. Secretion of hydrogen occurs in the proximal convoluted tubule and also by cells called intercalated cells in the distal convoluted tubule. And that's one of the more important ways that our body is able to regulate our pH balance. It's a way that our body can prevent the pH of our body fluids from becoming too acidic. Okay. There's three main mechanisms by which our body regulates pH. There's two physiological ones, and then there's also buffers that are found in our blood. Buffers are just chemicals that hydrogen ions bind to, and in binding to these substances, they get neutralized. But the kidneys is one physiological mechanism by which our body can get rid of excess hydrogen ions. The other way is via the respiratory system. By blowing off more CO2, you can lower the hydrogen ion concentration in the blood. The CO2, if it builds up in the blood, it combines with water to form carbonic acid, which breaks apart to form bicarbonate and hydrogen ions. Okay, so if you blow off more CO2 by increasing your breathing rate, then that also lowers hydrogen ion concentration. So actually, the kidneys are the most effective way of getting rid of hydrogen ions. So that can restore pH balance the better than any of the other mechanisms. So let's. All right, so then the next part of the nephron that we haven't talked about, let's see, how's our time going here? We're just about out of time, so let's see. I think this would probably be a good place to stop right here. So what we're going to look at next is we're going to look at how further reabsorption can occur in the nephron loop, and even more water can be reabsorbed and conserved by the body.